Hello all, I'm Yogesh Singh. Welcome to my YouTube channel, Yogi's Data Lab. Today we are going to talk about linear regression. That is the very first algorithm that we encounter when we talk about machine learning. So what is linear regression? When should I use linear regression? What is a best fit line? What is ordinary least squares method? The matrix of linear regression, and we'll also talk about the assumptions of linear regression. Now, when we talk about machine learning, we do know that there are two types in machine learning that we generally talk of, which is supervised learning and unsupervised learning. In supervised learning, the problem statement is classified into two parts. One is known as a regression problem, and the other is known as a classification problem. So what exactly is a regression problem? So whenever you are predicting any target variable which is continuous, we know that in supervised learning, we have a target variable. Means I am trying to predict some output. So I do have a target variable, or we call it as an output variable. Means I'm trying to predict some y, something that I want to know. Now, when your target variable or your output variable is continuous, like predicting the age of a product or number of shares your post is going to have, or price of a product, right? So these can be continuous values. Someone can be 23 years old. Someone can be 23 years, 4 months, 20 days, like this, right? So you see that I have data which is continuous. This is what I want to predict. When I talk about shares of a post, it can be like I can have 20 shares of a post. I can have 30 shares of a post. I can have 40 shares. I can have 500 shares of a post. For price, any product can price from $2 to maybe $2.2, can be even $2.57. You don't know, right? So these are all continuous values. So when my target variable is continuous and I want to use machine learning to do that, I will use the concept of linear regression. Having said this, let us also try to understand what exactly does it mean by linear regression. So when I talk about what exactly does it mean by linear regression, there are two terms here. One is linear, other is a regression. So linear, it is pretty much makes sense that when I say linear, linear means it is talking about a straight line. I'm talking about a straight line. I want the points to fall in a straight line. But what is a regression? Regression means moving towards the average. I might have multiple points scattered here and there. I want to have things moving towards the average of all these points. That is linear regression. Now, to understand this better, we will go through one example. Let us say that we talk about the multiplication table of 2. So 2 cross 1 is equal to 2. 2 cross 2 is equal to 4. 2 cross 3 is equal to 6. 2 cross 4 is equal to 8. If I have to plot this, how should I do this? If you notice here, this term is constant. This 2 is constant. This value keeps on changing. So let us say this is x and this is my output, which is y. If I have to plot this, so this is 1, this is 2, this is 3, and this is 4. I'll have 2, 4, 6, and I'll have 8. So I'll get a straight line, something like this, which will pass through the origin, where it says that whenever my x is 1, my y is 2, x is 2, y is 4, x is 3, y is 6. What do we derive from this? It means that if I talk about the equation of this line, I can say y is equal to 2x. So this is the data which was given to me. Looking at this data, I could derive an equation y is equal to 2x. But on the contrary, let us say that if you have points which instead of 2, 4, 6, and 8, you are given the values 3, 5, 7, and 9. So the equation or the line will also change, because for 1, y is going to be somewhere here. For 2, y is going to be somewhere here. And likewise, you'll get a straight line, something like this. And it will intersect your y-axis at this point, which is 1. Which means that whenever your x is 0, y is equal to 1. The equation of this line will be y is equal to 2x plus 1. So what does it tell you? It tells you that if I have some points lying here, the equation changes and I move the straight line up by 1 unit on the y-axis. So here in this equation, y is equal to 2x plus 1. This is known as the intercept. And this value is known as the slope. If you can relate this with your coordinate geometry where you studied y is equal to mx plus c. C is the intercept and m is the slope. And we can say that y is a function of x, and this function can be anything. If the values were 2, 4, 6, and 8, the function was y is equal to 2x. If the values were 3, 5, 7, and 9, the function was 2x plus 1. So depending on my x and my y values, I will get the function of x. And this function is what we have to derive in the linear regression. So in linear regression, what we do is we try to find an equation of a straight line given my x values and the y value. That is the whole purpose of linear regression. Now, what we saw is we said that y is a function of x, and we said that y is equal to 2x plus 1. When I talk about y being only dependent on x, x is known as the independent variable, and y is known as the dependent variable. These independent variables or variables, which we'll see ahead, are also known as predictors. Why? Because they are contributing towards your target variable, which is y. Now, let's not stick to 2x plus 1. Let's try to take it to the next level where we will talk about a business use case. Let's say I want to predict the price of home. Now, a price of home is going to be a continuous variable, and hence we are taking regression. Let us say that price is a function of area of a home. When I say price is a function of area of home, it means that we can plot it this way, where x-axis is your area and y-axis is your price. I can have any home of 1000 square feet. I can have 2000. I can have 3000. I can have 4000. I can have different area of the home. And based on this, you can also observe that there can be multiple data points. What do we observe here? We look at that as and when the area increases, the price of home also increases. So it shows that it is a positive correlation between the area and the price. However, in this situation, we have only considered the area of a home contributing towards the price. But it is not just the single variable which will contribute, right? There can be multiple variables which can contribute, like distance from school. So let's write it down. Distance from school. You can also have distance from market. Does it have a parking or not? Is it by the main road or not? Main road or not? Does it have a basement or not? So there can be multiple things which could be contributing towards the price. So I cannot say that Y or your price is just a function of your area. Ideally, price will be dependent on all these variables. So if I call this as x1, this variable as x2, this as x3, x4, x5, and x6, it means that my price is a function of all the 6 variables x1, x2, x3, x4, x5, and x6. So my job now when I do linear regression is to find out that equation which will justify the price with these variables. So we come up with a generic equation which is given by y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 up to beta 6 x6. If I generalize this, instead of beta 6 x6, I'll go ahead and write beta n xn. So this equation that you see over here is the equation of linear regression, where this is your intercept, and these values, beta values, are your coefficients, which we also call as slope for their respective independent variables. So this equation is what we have to identify given on a historical data. Now, let's talk about best fit line. Let us say that these are my data points. This is my X and this is my Y. And I have my points here. These are the points which have been given. Now, if I try to find a regression line, so someone might draw a line like this, like the black line. Someone can go ahead and draw it like this. Let's say the orange line. This is the orange line. And someone can draw it in a different color. Let's say this blue line. So how do you identify which one of these lines is the best line for your prediction? So that identification of which line is the best line is done using OLS method, or the ordinary least squares. So to understand ordinary least square, we need to understand what is a predicted value, what is an error, and how these squares are reduced. So let us take any one of these lines. So if we talk about this blue line, okay, so I'll take some other ink. If we talk about this blue line, you see the distance over here is high. Here it is low. Here it is some distance. But is this line, the blue line, having the least distance from the points, or is it the black line or the orange line which has the least distance from the points? Why do we do a square? Because some points are below this line and some points are above this line. If I don't do a square and I just sum up all the distances, the positive value will nullify the negative value. And the positive value nullifying the negative value will make it 0. But ideally there's a distance. So we do a square so that we can calculate the distances and see which one of them has the least amount of distance. So to understand this, we'll go with another diagram and try to understand what is a predicted value, what is an error, and how do we come up with the matrix around it to identify which one of them could be my best fit line. So let's draw this. So to understand this, what we are doing is we are assuming that this is one actual point corresponding to certain value of x, which means that at certain value of x, this was your y. At some value x1, this was the y. Now, I have a regression line which goes like this. I'll also have one line since I'm talking about the distances measurement, right? The square distances. So I'll go ahead and put a average line over here. So let us say this is your average line. When I say average line, it means the average of y. So y bar. So what is happening here? If you look at this equation, this is the equation which has been formed. Now, whenever I give it the value x1, it is always going to predict me this value because this is a mathematical equation which has been formed. So I'm always going to get this value of y, which is to be predicted when x is equal to x1. I have been able to predict little above the average and I have regressed it, and this distance will be y cap minus y bar. Why? Because this total is y cap, this point is y bar, so this remains as y cap minus y bar. What about this region? This is the part I missed to predict. So this is known as epsilon, which is given by y minus y cap. Means the actual value minus the predicted value, which is y cap, is epsilon. So I can say in a way that y is equal to y cap plus epsilon, which is the actual is equal to the predicted plus the errors. So this can also be written as TSS is equal to RSS plus SSE, which is total sum of squares. TSS is total sum of squares. RSS is regressed sum of squares. And SSE is squared sum of errors. However, whenever you are studying certain books, you will see that RSS is referred to as residual sum of squares. Some books refer RSS as residual sum of squares. When they are talking about residual, it is not the predicted value. They are actually talking about the squared sum of errors. So be careful whenever you are going through any content. Look at the RSS. What exactly is it talking about? Is it the regressed sum of squares, which means the predicted value, or is it talking about the residual sum of squares, which is the error value? Now, since we know that total sum of squares is equal to regressed sum of squares plus squared sum of errors, we can go ahead and derive a couple of matrix around this. Now, what are they? Let's see. So what we just said is TSS is equal to RSS plus SSE. Now, an important point here is the errors the least amount of value of the errors can be 0. Means I'm doing nothing wrong. It means that I'm able to predict everything as it was. This was y is equal to y cap plus epsilon. When epsilon is 0, it means that y is equal to y cap, means I have predicted everything accurately as it was. So whenever my errors are 0, my TSS comes equal to RSS. This gives birth to a concept known as coefficient of determination, which is known as R square, and R square is defined as RSS divided by TSS. Means out of the total values, how much variation I have been able to explain is my RSS. It's just the same way as I have given an exam of 100 marks and I've scored 80%, means I've been able to answer 80% of the questions correctly out of the 100 marks question paper. So regress sum of squares is the part where I have been able to predict the variation in the data, and TSS is the actual data which I had to predict. So the part which I was able to predict divided by the total data becomes the R square, which is coefficient of determination. And this can also be written as 1 minus SSE divided by TSS, which if you solve, it is nothing but TSS minus SSE divided by TSS. And we know that TSS minus SSE is nothing but RSS by TSS. So this is one important matrix that we talked of, which is known as R square. So R square tells you the quality of a model about how much variation you have been able to explain in the data with your model. But there is a flaw here. I'll not say a flaw, but there's a problem here. Problem is, I cannot go ahead and look at the number of rows and columns. I cannot control that, right? So this we'll see when we are uh, looking to the next video where we will talk about the matrix calculation. There's just the X variable and the Y variable. There's no count of how many columns have been used or how many rows have been used. So for this came the concept known as adjusted R square. So adjusted R square is given by 1 minus R square into n minus 1 divided by n minus k minus 1. N is the number of rows and k is the number of columns or features or variables, whatever you call them. Now, what is the benefit of this? Adjusted R square penalizes the unnecessary use of columns in the data, which can cause overfitting and give you absurd results. So adjusted R square and R square both can be used in a combination to determine the quality of a model where we'll always want that adjusted R square and R square should be close by. So you can say that adjusted R square and R square are the matrix which tell the quality of a model. However, we haven't yet talked about the errors in the data or how do we measure the errors. So let us talk about that. Now, to measure the errors, there are a couple of methods. One of the most commonly used method is known as the root mean square error, also known as RMSE. The other is known as mean square error, MSE. And then you have mean absolute error, given as MAE. RMSE. Now these are the matrix which measure the amount of errors in your model. Amount of errors. We'll always want that the amount of errors in any model should be low and the R square and the adjusted R square should be high. Why? Because we want to predict more of the variation in the data and have lesser amount of errors. So these matrix which you see here, RMSE, MSE and MAE, they always have to be low in number, while R square and adjusted R square should be high in number. Now, when I talk about root mean square error, mean square error and mean absolute error, how do we remember the formula of this, or how do we calculate it mathematically? It is pretty straightforward. Let's go right to left. For all of them, we'll go right to left. So the first term is error. What is error? It is y minus y cap. So this is done. What is the next term? It is square. So it's a square. What is the third term? It's mean. So it becomes summation by n. And what is the fourth term? It is root. So this is square root. So this is the formula for root mean square error. Similarly, you can do it for mean square error. It is y minus y cap whole square and the mean. Similarly, for mean absolute error, y minus y cap absolute and the mean. So you don't need to remember it. You just need to go right to left and you'll be able to devise the formula. And these will give you the amount of errors in a model, while R square and adjusted R square will go ahead and give you the quality of a model. So if I come back to the same problem statement where it all started, I can say that any model or any of the lines for a best fit line where the R square and adjusted R square is high and my matrix for errors, mostly what we use as RMSE, is low, is the best fit line. Having discussed this, we'll also talk about one more concept, which is known as multicollinearity. So let's talk about multicollinearity. So multicollinearity, what exactly is multicollinearity? So multicollinearity, it means the correlation of independent variables which are contributing towards a target variable. So it means that if one independent variable increases by 1 unit and the other independent variable increases by multiple units, that measurement is known as multicollinearity. So the impact of one independent variable on the other independent variable by multifolds is multicollinearity. And how do we measure multicollinearity? We measure multicollinearity by a concept known as variance inflation factor, which is also known as VIF. In case of variance inflation factor, as we'll see in the next video in the case study, we generally use a value of 5. Any variable having a value greater than 5 will be dropped since it is considered to be multicollinear. However, certain places you even take a value of 2 in case you have many variables in the data set, and you can go ahead and reduce your number of variables without compromising of the loss of data. You can still go ahead and use a VIF of 2. Or you're working on very critical projects where there can be some catastrophic losses that can occur due to the variation in the model. So you can go with a VIF of 2. However, majorly we work with a VIF of 5. So this was one concept of multicollinearity, which we will see in the case study how we use it. Now coming to the next topic, which is the assumptions of linear regression. Now, talking about assumptions of linear regression, a couple of books even say that multicollinearity, which we just discussed now, is an assumption of linear regression. But most of the books do not agree to it. It says that multicollinearity is not an assumption of linear regression. It is more of a need which needs to be done in order to remove variables which are multicollinear to avoid overfitting or the curse of dimensionality. However, when we talk about the assumptions, these are the four assumptions which we generally talk about: linearity, normality of errors, homoscedasticity, and independence of errors from predictor variables. These are the four assumptions of linear regression. Now, what do they mean? So let's take them one by one. So when I talk about linearity, we do a check by plotting the predicted y on the x-axis and the errors on the y-axis. What we want is that the average error should be approximately equal to 0 and your errors should be plotted something like this. The average line of your errors, which you'll see now, should be parallel to your x-axis. What does this mean? It means that if my errors are approximately 0 and throughout my predicted values, my average errors is 0, which means if I look at y is equal to y cap plus epsilon, and epsilon is approximately equal to 0, which means that my y is approximately equal to y cap. If my y is approximately equal to y cap, if I draw a line, I should get a straight line between y and y cap, which means that I have achieved the linearity and all my x variables are linearly contributing towards my target variable y. That is linearity. Talking about the next one, which is normality of errors. So let us say this is again x and this is y. I have this regression line. Okay. Now with this regression line, for a certain value of x, I had different values of y, which means that there is going to be error here. There are errors for this value of x. There are errors for these y. How do they come? Let's say x is equal to 1, where actual y is 2, x is 1, y is 3, x is 1, y is 2.5, x is 1, y is 3.5. And you end up predicting y cap as 3.25. So this is the same situation. For x is equal to 1, I have different values of y. And I have my errors because I have predicted it to be 3.25. So the errors that are coming here will follow a normal distribution. Similarly, for some different value of x, the errors will follow a normal distribution. Similarly, here it will follow a normal distribution. So since throughout my regression line, I see that I am having a normal distribution, it means that across all the points in my regression line, it is going to follow a normal distribution. That is normality of errors. Coming to the third point, which is homoscedasticity. When you talk about homoscedasticity, this means constant variance of errors. Now, when I talk about constant variance of errors, if I talk about a normal distribution and my mean is approximately equal to 0, which is in analogy to what you saw in a standard normal distribution, where your mean was 0 and the standard deviation was 1. That is standard normal distribution. Here, if I take the similar analogy and I say that my mean is 0 and I have a normal distribution, it means that I am going to have a fixed standard deviation from the mean of my values, which is nothing but my errors. If my standard deviation is fixed, it means my variance is constant, and that is nothing but homoscedasticity. And the fourth one is independence of errors from the predictor variables, which means your x variable should not contribute towards your errors. Means your x's or your predictor variables or your independent variables should not control your errors, which means if your x increases, the error reduces, or x increases, the error also increases. This should not happen. So this is what is independence of errors from predictor variables. How do we test this? What are the tests that we do? How do we check these assumptions of linear regression? We'll see it in the next video when we talk about the case study. This is all we have on linear regression to understand what it is, how you go ahead and identify your best fit line, what is OLS, what are the metrics that we require, and what are the assumptions. If you like this video, please go ahead and like it, share it, and subscribe the channel. See you again in the next video. Thank you.